All right, sorry about that. I got cut off right at the end last time. What I was saying was that the equation that we will learn for the period of a pendulum is an approximation. It only really works if the pendulum has an angular displacement to either side less than 30 degrees. So the reason that this approximation works is because the period is actually not proportional just to the angle itself, but proportional to the sine of the angle. And if you were to take the value of the sine of an angle and compare that to the actual angle in radians, you'll find that up to about 30 degrees, they're very, very similar, but then they start to deviate pretty noticeably after that. So that's called the small angle approximation. You just basically have to recognize that if you're asked to find the period of a pendulum, then the equation that we will learn, which could be based on one of these three factors or maybe something else we haven't listed, the equation that we will learn is only valid if the maximum angular displacement from equilibrium is about 30 degrees. Okay, so again, in class we'll look at the actual equation. We'll kind of derive that and experiment with it. What I want to close with is some statements about how the different quantities that we've looked at, position, velocity, acceleration, energy, force, how they relate to where the object is in its motion, because you'll notice some similarities as you look at all of these different examples. So let's start with position. For the pendulum and for the horizontal spring, we said that the equilibrium position is what we would call the zero position, the origin, and then the turning points are the maxima and minima for the position. So in other words, for the pendulum up here, this is one of the turning points. It's also the maximum height and the maximum distance, maximum x position. Okay, the minimum or the equilibrium is the zero position down here. The only situation for simple harmonic motion that we didn't really say this for was for the vertical spring. We said that the equilibrium was not the zero position. We said the zero position was the lowest point. That was really just because we're used to setting the lowest point as where gravitational potential energy is equal to zero, so that's what we did there. But it would have been no problem at all for us to move the gravitational potential energy 0 point up to the equilibrium position. So that's just a matter of choice that we used. How did the velocity relate to these different points? We saw in all these examples, and I encourage you to go back and look at these, we saw in all these examples that the velocity was highest at equilibrium, and it was 0 at the turning points. And that makes sense. At the turning points, in order for something to change direction, it has to have a velocity that passes through 0 momentarily. And at the middle, where there is no acceleration to keep speeding it up, and there's also no acceleration to slow it down any farther, the velocity is at its highest. The acceleration was kind of the opposite of that. The acceleration was 0 at equilibrium, because remember, at equilibrium there are no forces. There is no, excuse me, I shouldn't say that. There is no net force acting on the object. So if at equilibrium, if the net force is 0, the acceleration has to be 0. So actually I'll fill that in here as well. The restoring force is 0 at equilibrium. And the acceleration was the highest at the turning points. These were the places of maximum displacement from equilibrium. And these are true no matter if you're looking at springs or pendulums. The kinetic energy goes along with the velocity because kinetic energy's equation is 1/2 mv squared, so that goes right with the velocity. As the velocity goes, the kinetic energy goes. The kinetic energy was highest at equilibrium because the velocity was the highest there. And it was 0 at the turning points where the object wasn't moving. Okay. Oh, and for the restoring force, this was the highest. Since the acceleration was highest at those points, the restoring force was also highest at the turning points. And last but not least, the potential energy. Again, for the vertical spring, this was a little bit different because we made our 0 point not at equilibrium, but we very easily could have for the gravitational potential energy. In general, the potential energy is 0 at equilibrium. think about the horizontal spring when it's not stretched out at equilibrium. It can't have any elastic potential energy, and the pendulum at equilibrium has zero gravitational potential energy. And the potential energy is highest at the turning points. This is where either the spring is the most stretched out or the bob is the highest up that it has been, or that it will go. So these are in general how these different quantities vary when you have an object in simple harmonic motion. And this will come in handy as we look at different situations involving springs and pendulums. Again, all of this stuff, with the exception of the equations for period of a pendulum that you will learn, all of this stuff we could have put into the previous units. But it's a good idea to look at simple harmonic motion by itself, not only because it's a new type of motion that you haven't really looked at before, but also because it's a good review of all these other topics we're hitting on: kinematics, forces, energy. There might be some problems that involve momentum. There could be some circular motion tie-ins. Everything that we've done so far is kind of recapped in simple harmonic motion. The reason we do it now is because some of our other units, we're going to take kind of a short break from doing mechanics as you guys are used to it, and we're going to move on to some other units now, and then we'll come back and hit a couple more topics at the end of the year. But this is a good kind of review for the middle of the year to kind of tie everything in together at this point. So that is it for the notes on simple harmonic motion. I'll be back in the next unit, which will be on waves. See you later.